Our lesson today is about counterexamples. Counterexamples is a concept that you will encounter over and over and over again in your high school math courses. All it means is if you make a mathematical statement about something, if anybody can find even one example that contradicts that statement that you made, then you can conclude that that statement is false. Okay? So a counterexample disproves a statement. Okay, so here's a statement. All circles are shaded. Well, right away we can see that, yes, this circle is shaded, but this circle is not shaded. So this not shaded circle would be called a counterexample because it disproves our statement, shows us that this statement is not true. Here's another statement. All words start with the letter B. Okay, well, the key to this statement is that we're talking about words. Okay, well, the word bat does start with the letter B. The word boat starts with the letter B. These examples strengthen our argument. They confirm our statement, strengthen it. However, this word cat right here begins with the letter C, not B. This would be a counterexample because it proves that statement false. These ones would not even count because they're not words. Okay, here are 5 statements. We need to figure out which of these statements the name Bob would be a counterexample for. Okay, so the first statement says, all names have 3 letters. Well, Bob. This is an example that confirms this statement. It's a name that does have 3 letters. Okay, so not a counterexample. What about the second statement? All boys' names start with D. Well, Bob does not start with D, and it's a boy's name. This is a counterexample proving this statement to be false. All boys' names do not start with D. Number 3, all names have 4 letters. Well, again, Bob contradicts that because it's a name that has 3 letters. It proves that this statement is false. It's a counterexample. All names are boys' names. Well, Bob is a boy's name. So it actually is not a counterexample. It strengthens that statement. All names read the same backwards as forwards. Well, again, Bob does read the same frontwards as backwards. So that statement proves or strengthens our argument. The only 2 statements there where Bob is a counterexample and proves the statement false would be these 2 statements here. All boys' names start with the letter D, and all names have 4 letters. Here's another statement. All cards with an odd number have a vowel. Okay, well, let's see if this is true. Let's find all the odd numbers first of all. 7 is odd, 5 is odd, 1 is odd, 5 is odd, 11 is odd, 9 is odd. Those are all the odd numbers. Okay, do they all have a vowel? Yes. This is an I. Yes. This is a K. Oh, that's not a vowel. J. That's not a vowel. U is a vowel. So some do and some don't. But because we found these 2 counterexamples, that means we've proved this statement is false. Okay, this time we're going to see if we can use what we've learned about prime numbers to find counterexamples to this statement. All cards with lowercase letters have prime numbers. Okay, first of all, let's remember what prime numbers are. Think about that for a minute. How would you define a prime number? Prime numbers have only two factors, 1 and themselves. Okay, so let's look for prime numbers. 7 is a prime number. The only way to make it is 1 times 7. 6, nope, not a prime number. 1 times 6 or 2 times 3. What about 5? 1 times 5, the only way to make it. So 5 is prime. What about 1? I hope you remember from last day that 1 is not a prime number because it only has one factor, and that's the number 1. 1 times 1. Okay, what about 5? Well, we've already determined that 5 is a prime number. Its only factors are 1 and itself. What about 11? It is a prime number. Its only factors are 1 and 11. 9? No, I can make 9 with 1 times 9, 3 times 3, not a prime number. What about 4? 1 times 4, 2 times 2, not a prime number. 8? No, 1 times 8, 2 times 4, not a prime number. What about 6? 1 times 6, 2 times 3, not a prime number. Okay, so we have found all the prime numbers. I've marked them all in red. Okay, now our question said, all cards with lowercase letters have prime numbers. Okay, so let's look. A lowercase letter on this card? No. Counter example. Lowercase letter, that's a lowercase. No, that's a capital I. So again, another counter example. Lowercase j, lowercase k, those ones are okay. But the two that I've circled are counter examples proving that statement that all prime numbers have a lowercase letter on them. False. Our other statement says all cards with perfect squares have consonants. Okay, well, let's review again what a perfect square is. Think about that for a minute. A perfect square is a number like 25 because it can be written as the product of two identical factors, like 5 times 5. Okay, so looking at our numbers on our cards, which ones can be written as the product of two identical factors? Not 7, because it's 1 times 7. 6, 1 times 6, 2 times 3, nope. 5, 1 times 5, nope. 1, 1 times 1, okay. So 1 would be considered a perfect square because it can be written as the product of two identical factors. What about 5? We've already determined it's not a perfect square because the only way to make it is 1 times 5, not two identical factors. What about 11? 1 times 11, nothing else. Nope. 9? Yes, 9 can be written as 3 times 3, two identical factors. So yes, 9 is a perfect square. What about 4? Right, 2 times 2, two identical factors. 8, 1 times 8, 2 times 4. Those are the only factors of 8. None of them are identical. What about 6? 1 times 6, 2 times 3. 8, nope, not identical factors. Okay, so we have identified that we have 3 perfect squares, 1, 9, and 4. And our statement said all cards with perfect squares have consonants. So let's check and see. Ooh, that's not a consonant. A consonant is any letter in the alphabet that's not a vowel. Well, that is a vowel. A, E, I, O, U. So this is a counterexample. That is not a consonant. Also, this is another counterexample. U is a vowel, not a consonant. So we have found 2 counterexamples that prove this statement to be false. Here's another statement. All girls are teenagers. That may or may not be a true statement. Obviously it's not, because we can probably find or think of counterexamples. Can you think of a counterexample, an example of that would make that prove that statement is false? Oh, well, how about this one? Mrs. Baker. I'm not a teenager. I'm a girl, but I'm not a teenager. Okay, or what about your little sister or your little cousin, right? Any example you can think of that proves this statement false is a counterexample. Okay, we've listed 2 of them there, but there's lots. Okay, what about this second statement? All teenagers are girls. True statement or not? Well, let's think of counterexamples. Here's one. Boys. Right? There's a counterexample right there, proving this statement is false. All teenagers are not girls. Boys are teenagers too. What's the same and different about these 2 statements? All girls are teenagers. All teenagers are girls. These are reverses of each other. These are reverse statements, okay? We've just flipped the order of them. Sometimes you will find that a statement is true, but its reverse is false. Or sometimes you'll find that a statement is false, but its reverse is true. Okay? They don't mean the same thing though, do they? Okay, so here's a statement. All carrots are vegetables. Is this a true statement? All carrots are vegetables. Is the reverse true? Well, what would be the reverse? All vegetables are carrots. Is that true? Are all vegetables carrots? No. Okay, it's false. So sometimes the original statement may be a true statement, like this one was, but its reverse is false. We're going to see if we can write the reverse of each true statement below, and then we'll decide if the reverse is true as well or not. Okay? All triangles are polygons. Okay. Remember the word polygon. Poly just means many sided. Okay, so this is a closed shape that has many sides. Okay, so all triangles are polygons. That's a true statement. That's the smallest polygon you can have, a 3-sided polygon, but that is true. All triangles are a closed 3-sided shape, a polygon. Okay, is the reverse true? Well, what would be the reverse? All polygons are triangles. Well, is that true? If a polygon is just a many-sided closed shape, then a square is an example of a polygon, and a pentagon, 5-sided shape, is another example of a polygon, and an octagon, like a stop sign, an 8-sided shape, is another example of a polygon. Are all polygons triangles? No, that's false. So we came up with 3 counterexamples. So a counterexample would be a square, or a pentagon, or an octagon, or any other closed, many-sided shape. Let's look at this example at the bottom of the page. All squares are shapes with 4 equal sides. Okay, what would be, let's see if that's a true statement first. All squares are shapes with 4 equal sides is true. What would be the reverse? All shapes with 4 equal sides are squares. Well, is that true? Can you think of a counterexample that would prove this statement not true? Can you think of any shapes with 4 equal sides? Well, I've got a shape like this. I could have 4 equal sides. Is that a square? It's called a rhombus. And that's a shape with 4 equal sides. But it's not a square. Or a shape like this. I could have a parallelogram with 4 equal sides, but it's not square corners. Those are both counterexamples that prove that statement false. What about this one? All numbers with 1's digit 0 are even numbers. Okay, so we can think of quite a few examples of this. This would be things like this. 1's digit that's 0, so 20, or 30, or 80, or 70. Okay, any number that has the 1's digit 0 is an even number. Okay, that's a true statement. All of those are even numbers. They can be divided by 2. What would be the reverse of that statement? All even numbers have 1's digit 0. Is that a true statement? Do all even numbers have a 1's digit that is 0? Well, no. Can you think of some counterexamples? How about 2, 4, 6, 8, 12, 14, 16, and we could go on, couldn't we? All of these numbers are even, but they don't all have 1's digit that is 0. Right? Okay, so the original statement was true, its counterexample is false. Its reverse is false. Okay, what about D? All people are mammals. Well, that's true. We are all mammals. The reverse of this? All mammals are people. Is that true? No. Can you think of a counterexample that would disprove that statement? Think of a mammal that is not a people. Well, monkey, dog, anything you could list that would be a mammal that's not a people would be considered a counterexample. So that proves that the reverse is false. Hey, what about all girls are people? What's the reverse of that? All people are girls. True or false? Well, the original statement, all girls are people? Yeah, that's true. Are all people girls? No. Can you think of some counterexamples? Well, boys, men. As long as you can find even just one counterexample, it proves that statement false. All dogs are animals with tails. True statement. Or maybe not. Do all dogs have tails? I think so. Generally speaking, I think that's true. Okay. What about the reverse of that? All animals with tails are dogs. Is that a true statement? Can you think of a counterexample? An animal with a tail that's not a dog? Well, how about a kangaroo? A fox? A deer? Okay, any example you can think of that disproves that statement. And those are just a few. There's lots. All humans are animals with legs. Well, that's true. We are an animal with legs. Okay? Okay, let's reverse that statement. All animals with legs are people, or are humans. Is that a true statement? All animals with legs are not all humans. Can you think of a counterexample? Well, monkey, horse, cat. Any of those would work. All right, let's see if you can think a little deeper. All spiders are organisms with 8 legs. That's true. So now we know it's a spider. It has 8 legs. Okay, let's reverse that statement. All organisms with 8 legs are spiders. Is that true? Can you think of an organism with 8 legs that is not a spider? How about an octopus? That would be a counterexample. That's an organism with 8 legs. It's not a spider. Okay, here are some for you to try. I'd like you to take out a sheet of paper, pause this video at this point, and see if you can make up a true statement whose reverse is false, and then a false statement whose reverse is true, and then a true statement whose reverse is true, and a false statement whose reverse is false. You will be handing that paper in to me at the end of watching this video. Once you're ready, restart the video for the last slide. The last slide says, Alana thinks that if n is a prime number, then 6 times n minus 1 will also be prime. And we have to try and find a counterexample to prove her wrong. Our hint is, we're going to check all the prime numbers in order. So remember, prime numbers are the numbers that only have 2 factors, 1 and themselves. So 2 is a prime number, 3 is a prime number, 5 is a prime number. We're going to try all of those in this expression here and see if the answer we get is also prime. Okay, so 6 times whatever n is minus 1. Okay, if our n is 2, we're going to sub in a 2 where that n is. So that means 6 times 2 minus 1. What does that give us? 6 times 2 is 12 minus 1. 12 minus 1 is 11. Is 11 also prime? Okay, yep. So when n is 2, it strengthens this statement that Alana makes, that if n, 6n minus 1, if she puts an n in there as a prime number, that answer would also be prime. Okay, let's try an n of 3. So 6n minus 1. So this time our n is 3. We're going to substitute it in where n is. So this means 6 times 3 minus 1. 6 times 3 is 18 minus 1. 18 minus 1 is 17. Is this strengthening Alana's statement that she thinks her answer will also be prime? Yep, 17. The only way to make 17 is 1 times 17. So far, her statement is proving to be true. Let's try an n of 5 in this expression, 6n minus 1. This means 6 times whatever n is. If our n is 5, that's 6 times 5 minus 1. 6 times 5 is 30, minus 1 is 29. Is 29 prime? The only factors of 29 are 1 times itself, so yes it is. Okay, what would be the next prime number? The next number after 2, 3, and 5 that would also be prime, that we can only make with multiplying 1 and itself. Well, the next one would be 7, right? So let's plug an n of 7 into this expression. 6 times 7 minus 1. 6 times 7 is, right, I hope you came up with 42 minus 1. That's 41. The only factors of 41 are 1 and itself. Okay, what would be the next prime number? 8 is not prime because it has more factors. 9 is not prime. 1 times 9, 3 times 3. 10 is not prime. 1 times 10, 2 times 5. 11 is prime, so our next prime number would be 11. Let's try this one. 6 times 11 minus 1. That would be 6 times 11, 66, minus 1, 65. Is 65 prime? Ooh, 65 is not prime, because I can make it with 1 times 65, but I know because it ends in a 5 that it's going to be 5 times something as well. 5 times 13. Okay, so no, 65 is not prime. So we have found a counterexample. When our prime number is 11, in this expression, our answer is not prime. So this statement is false. Okay, that is the end of our video for today. There is an assignment that you will be working on to go along with this video and then handing in at the end of class today.